Hi guys, welcome to our channel of Sciences and Mathematics. Our topic of discussion for today is going to be enthalpy of displacement. Now, displacement is one of the chemical processes whereby we find that metals maybe higher in the reactivity series are able to displace other metals from their solution, which are lower in the reactivity series from the solution form. An example of that is the one that we have given on the board, where we are trying to react zinc and copper sulfate solution. And we're going to see also that it's going to be accompanied by change in energy that we have already been talking about, the concept of enthalpy. So in this case, this is going to pertain the enthalpy of displacement, which we are going to discuss, of course, using the demonstration that I've given on the board. So without further ado, thank you and welcome. So as I've said, our topic for discussion for today is enthalpy of displacement. As I've said, displacement is one among many reactions that we encounter in chemical reactions. In a discussion of electrochemistry, we talked about the concept of zinc and copper, whereby if we have a reaction of zinc which is being placed in a solution of copper, then zinc is going to displace copper from its ionic state, and it's going to form a solid, which we are going to see later. Maybe I can just mention there's going to be a brown deposit of copper in this specific case, and that one implies that there's been a displacement which has taken place. Now, this particular kind of process is accompanied by change in energy, which basically we refer to as enthalpy of displacement. So therefore, that demonstration for ours is the one that we're going to use to try and figure out how we can be able to find enthalpy of displacement. So therefore, from our demonstration, we're going to use 100 centimeters cubic of 0.5 molar copper sulfate solution and 4.0 grams of zinc, and we're going to react them and try to see what happens. So in this case, from the sample results that I've given for the change in temperature, we are going to see that this is initial, this is final. We're going to see that the temperature change from initial to final, there is an increase in temperature by 24.5 degrees centigrade. So this implies that whenever there is an increase in temperature, the system is dissipating heat away, to the surrounding, and therefore this one entails an exothermic reaction. So therefore, those are some of the concepts we can be able to just identify as per our observation. So therefore, I say that there's also going to be an observation in a sense that after the final result, after stirring the solution, after the mixture of zinc has been placed into the solution and then stirring, a reading for the final temperature when the experiment is complete, there will be some brown deposits of copper solid, of copper elements which are deposited at the bottom of that specific beaker. So therefore, the resulting solution, this is an ionic equation that I wrote, so it's going to form zinc sulfate as the final solution in that case. So having been given the concentration of that specific solution we're working with, we can be able to work out the number of moles of zinc that was used in this experiment. So therefore, I'm just going to write a stoichiometric equation for the reaction that is taking place there so that we can be able to use it. So we have zinc solid reacting with the copper sulfate to form zinc sulfate plus copper. So let's try to see whether we can be able to, we have a balanced equation. I think this is balanced, okay. So from this we can see that the moles of zinc used is equivalent to the moles of the copper sulfate, the copper ions. So since we have the mole ratio of the reactants 1:1 and of the products 1:1. So therefore, if we have 0.5 moles in 1,000 centimeter cubic of a copper sulfate solution, the mole ratio between this and this is just 1, but the solution that was used of this specific concentrated solution of copper sulfate was 100, so therefore it's going to be 0.5 1000. So this is over 10.05 moles, of course, of copper ions that were used in this specific experiment. So therefore, we can be able to calculate the number of moles of zinc having been given the mass of zinc that was used in this case. So therefore, we can be able to calculate that by dividing the mass that was used, mass in grams, divided by the relative formula mass over that specific element, 65. So we're going to kindly check on this. So we're going to find that it's 0.065 moles of zinc that was used in this particular experiment. Now, in trying to compare the number of moles that were used, that were present, and trying to see the number of moles that were used in this particular case, we are seeing that there's a difference. We said that the mole ratio is the same, 1:1. There's a difference in the number of moles of zinc that were introduced and the one that was used, bearing in mind that this is in relation to the mole ratio that we have said. There's a slight difference of around 0.01. So therefore, we can account for this change in the number of moles that were used in this particular case later. But in this case, we're going to see that we're interested in the amount of heat, that is the enthalpy of displacement, that we're going to calculate from this particular experiment. So in this case, this is just an additional information that we are trying to relate to, having been given the concentration of that specific solution. So in any case, we are asked for a molar enthalpy of either of those. We can be able to state or maybe have an idea how we can be able to handle that. So we were talking about the molar enthalpy of formation, which we said we can be able to give it as MC delta T, mass, specific heat capacity, and change in temperature. So we said this one we're going to take the value for water, which this is per kilogram per Kelvin. We're going to take that reading for water, therefore we're going to do a substitution for that. So therefore, in us to find the molar enthalpy of formation, it is going to be the mass. We use the mass of water there in form of kilograms. So assuming the density of water is 1 gram per centimeter cube, therefore that is going to be 0.1 kg times 4.2 kilojoules per kilogram per Kelvin times the change in temperature, 24.5 kelvins. So this is going to give us a 10.29 kilojoules. So having seen that heat was dissipated from the system into the surrounding, therefore we are going to have a negative value for that specific kind of temperature, to denote that it's an exothermic reaction. So from this we said that 0.5 moles of copper are used to displace zinc from its ionic form. 0.5 moles of copper are displaced from their ionic solution by zinc, and the amount of heat that is involved is the one that we have already calculated. So therefore we can do a comparison and say this is 0.05 moles, and we say the mole ratio is 1:1, dissipates 10.29 kilojoules of heat. So we want to find 1 mole. Will dissipate what amount of heat? So this is 1 times 10.29 divided by 0.5. So this is going to give us 205.8 kilojoules per mole. So this is going to be a negative value, as I said. The molar heat of displacement, therefore, for zinc is going to be given as that. So this, having said that, we said that we can write so for us to show this particular change in heat, we can write a stoichiometric equation for displacement for this particular case, like the one that we have later written above, and try to show the change or the molar heat of displacement in this case. So I'm just going to do away with this, having written that figure down there. And after this, we're going to be accompanied by this simple change in enthalpy, or maybe you can just place it here. Change in enthalpy, which is a molar heat of displacement for that particular reaction, is going to be negative 205.8 kilojoules per mole. So this is the procedure that we can be able to use in order to find the enthalpy of displacement of this kind of a reaction that involve copper being displaced from its ions by zinc, due to the fact that zinc is high in the reactivity series as compared to copper. So we're going to see similar behavior of metals, especially in the concept of electrochemistry and other topics, which are trying to display this kind of a behavior. And in that case, I think we have come to the conclusion to the conclusion of our discussion, and I hope that maybe if we come across this kind of a problem, so first try to find out from the stoichiometric equation, especially having been given the concentration, how we can be able to find the mole ratios, and therefore that is going to assist us to find the quantity set in mass or maybe in grams of the reacting species and the product. And therefore we are going to do a comparison with the mass that is provided in order to find the number of moles that can be able to dissipate or take in heat by using this formula for MC delta T. And we say this one normally for solutions like this, we use the heat, specific heat capacity for water, which is a constant that we have been using for our experiment. I mean for experimental demonstration or the sample results, like the one that we have been given on the board. So I hope that we have understood how we can be able to find the enthalpy of displacement of reactions, reactions like the chemical equation that we have given for ionic, for ionic or maybe stoichiometric equation that we have used for copper and zinc as the one on the board. And given such a kind of a challenge, as I can conclude, of course, we've said that we can be able to use the formula that I've written here in order to find the specific heat which we are required to calculate. So that is it for today. Bye. God bless you.